And now we're going to go to some examples to explain to you what Bayesian statistics is and yeah, why a lot of statisticians think that, especially for small sample sizes in certain cases, it is superior to frequentist statistics. Okay, so another small quiz. Let's say that I have a self-test for the coronavirus, and 1,000 symptomatic individuals take this test. Now, here we have the results. We have people who have confirmed infection, maybe with PCR or something, and we have people for which the self-test was positive, and we have individuals for which the self-test was negative. Now, the question, what is the chance of getting a positive test result if you are infected? So if you really have the coronavirus, what is the chance that if you take a self-test according to these data, that the test will be positive? Yeah, so take a minute or two, you can talk with each other, and then we'll go to the answer. Okay, raise your hand if you have a solution. Okay, I'll wait another minute. Okay, same question. Could anyone raise their hands if they figured it out yet? We have one answer, two, three. Okay, who would like to give it a shot? Yeah? Okay, so let me repeat that here in front of the microphone. So there are 40 positive infected and 10 negative infected. So that's 40 out of 50 is 80%. Anyone got a different answer? Oh yeah, let me show the, the answers. Anyone who thinks this answer is wrong? No? Okay, very good. Answer is indeed 80%. How do you calculate it? Yeah. So the trick is to only look at these data. It doesn't matter what is the case for uninfected people because we have conditioned on being infected. So you only have to look at the column of infected individuals, and then you can calculate like this. Now, if you didn't figure that out in 3 minutes, or if you got it wrong, yeah, if this were mathematical education, I would scratch my head a little. But actually, a lot of clinicians don't get the right answer. There have been many studies done on this, and very often people answer this incorrectly. And we'll get to a couple of examples where people will generally give the wrong answer, yeah, unless they know the correct way to calculate it. Okay, so what if I flip it around? What if I say someone tests positive and I want to know the chance that this person is infected? How do we calculate it then? Yeah?
89%, I think 40, over 45.
Yeah, okay, 89%. So anyone disagree? Okay, good. Yeah, so how did you do it?
They add up the positives, there are 45 total, of which 40 are infected, so 40 over 45 is 80.89.
Yeah, very good. So the trick again is to first look at the condition. We're saying what is the chance of infected given a positive test result? So we only look at the case of positive. We completely ignore the negative case. And yeah, the way that works then is to look in the row of the positives and then divide the number of infected by the total, which gives you about 89%. Yeah, any questions so far? Okay, good. Yeah, because this is important to understand this lecture conceptually, the idea of conditional probability. There is a certain base rate that anyone in this room has the coronavirus at the moment, but if the test result is positive, then the chance changes dramatically because we have a condition. Yeah, so conditional probability is an important concept. Now, another example. Let's say that the year is not 2022, and you as a student, you lost a lot of weight due to my drawing skills, but also you acquired a house. And your house has one door and one window, and you want to go shopping. But there's a problem because, you're wondering, what if it's going to rain? Then I don't want to do shopping. So you want to estimate the probability of rain on a given day. Now, there are a couple of possible scenarios here. First off, you can only look out the window. So you can see if on this side of the house it's raining or it's cloudy, but you don't see anything else. Yeah? Okay. Well, this is what it looks like when it rains, and you can observe that it rains because you can see it out your window. And this is the Netherlands. You should have chosen a different country if you don't like this, but the probability of rain on any given day is a half. Okay, we also have the chance that it's just cloudy, but not raining. So again, you shouldn't have picked the Netherlands. That chance is even higher at about 2/3. Yeah, so on any given day, if I look out my window, I can see clouds. There's a 2 out of 3 chance that it is cloudy on any given day, and a 1 in 2 chance that it's rainy on any given day. Now, this can also happen. It can be cloudy without me observing that it's cloudy because, from my window it looks okay, but as soon as I walk out the door, there's clouds. And also, if it's windy, it could be raining, even though I don't see any clouds. Yeah, so it's possible for there to be rain, but no clouds from my perspective. Okay, yeah, but this is kind of rare. Has to be windy enough. There has to have to be clouds, specific location. And you have seen this many times because you live in the Netherlands for over a year now, and you concluded that this only happens 5% of the time. Now, okay, fast forward to today. It's again cloudy because it's the Netherlands. And I want to know, it is cloudy. What is then the chance of rain? Yeah, with the information that we just received. Okay, so let me sum it up. It rains half of the time. It is cloudy 2/3 of the time. And if it rains, almost always it's also cloudy, but not always. 95% of the time when it rains, it's cloudy. Okay, what then is the chance of rain if it is cloudy? This one's a little bit trickier, so let's take 5 minutes. You can talk with each other, and then at 9:30 we'll go to the answer. Okay, has anyone figured it out yet? Okay, we have one answer, two. Okay. Who thinks it's 95%? Okay, great. Who thinks it's half? 2/3? 1/3? Okay, at least we all agree the answer is not simple, I hope. You had an answer?
Yeah, the answer is 71.25%. The reason for that is that given, like, there is a probability of range one and two, but really those are two separate probabilities. There's probability of range given that it's cloudy, and there's probability of range given that it isn't cloudy. And you really only want the one that says chance of rain given that it's cloudy, which is 95% of the time raining is also cloudy. So then the probability of rain you can replace by saying actually that's 95% of half, which is 47.5%. And then also you say, all right, well, we know that it's cloudy, and so given the chance that it's cloudy, we're looking at normally, half out of 2/3 is 75%, but actually it's slightly less. It's only 47.5% out of 2/3, which is 71.25%.
All right.
Multiplying 95% by 75%.
Did you get the same answer? Yeah? Okay, very good. So, do you know what this law is called? It's okay. It's called the law of total probability. So, very aptly put, the trick here is to consider the fact that there are two probabilities of rain, two conditional ones. There's the probability of rain when it isn't cloudy, and the probability of rain when it is cloudy. Yeah? So, before I show the answer, let me give you another example where the differences are a little bit more extreme so we can see why any other answer is wrong. So, this has to do with what's called the base rate fallacy. And it goes as follows. Let's say that we have a breathalyzer and we stop a driver and yeah, we test whether he's drunk. And yeah, this device is pretty accurate. It never fails to detect drunk drivers. So if you are drunk, you will get caught. But it also has a false positive rate of 5%. Now, finally, yeah, there is some rate of drivers which are drunk. So if we screen randomly, there's a certain chance that we get a drunk person, and that happens to be 1 in 1,000. Okay, now this is the fallacy. A lot of people, when prompted this question, would answer that if the test only makes mistakes 5% of the time, then there is a 95% chance that the driver is actually drunk. And yeah, that's wrong. That is what's called the base rate fallacy. Now, let me show you why it's wrong. Because we have different rates that we have to incorporate. The chance of drunk, given that you're positive, is actually the chance that you get a positive test given that you're drunk times the probability, the base rate, that you would be drunk in the first place, because only 1 in 1,000 drivers are drunk. And then finally, we have to divide by the chance that any given test would be positive. Now, that last one is a little strange, the chance of a positive test, period, because, yeah, how do you calculate that? Well, again, we use the law of total probability to say there's either a test on someone who's drunk or a test on someone who's sober. And for one, the probability is the test that you're positive given that you're drunk times the prevalence of drunk people. And the other is the chance that the test is positive given that you're sober times the probability that you encounter a sober person. Now, those you can all plug in from the text to get the chance of a positive test, which is yeah, 1 because the device never fails to detect drunk people, times 1 in 1,000 because only 1 in 1,000 drivers are drunk, according to the story at least. And finally, we have the chance of a false positive, which was stated to be 5%, and the chance that you encounter a sober person, which is 99.9%. Now, if you Multiply that and add that up, you end up with a positive test probability of about 5%. Now, then we can plug in everything else, and we get 1 times 1 over 1,000 divided by this 0.05 more or less, which is only 2%. So definitely not 95%, not even 5%. It is way, way lower than that. Now, let me give you one more example, the one I just gave you. So let's say that there's a 95% chance that it's cloudy if it rains. You cannot say this. You cannot say, therefore, if it's cloudy, there's a 95% chance that it rains. This is the base rate fallacy. It is to assume that you can flip conditional probability by exchanging the condition and the thing we're trying to compute a probability for. The chance that it rains given that it's cloudy is not the chance that it's cloudy given that it rains. Yeah? Okay, so how do we calculate it? Same way, we have the probability that it's cloudy given that it rains. That was stated in the question, was said to be 95%. We said that half of the time it rains and 2/3 of the times it's cloudy. So if we plug that in, we get the correct answer of about 71%. Any questions? Okay, so this is the most important part of this lecture, because this is what is at the fundament of what makes Bayesian statistics, because this principle of multiplying a conditional probability when you have the opposite available to you is called Bayes' rule. Now, let me show you why this is so important for this course. I'm going to show you yet another fallacy. If the null hypothesis is true, the chance of obtaining this result is less than 5%. That's a significant p-value. I think we can all agree, right? But this you cannot say. There is a 95% chance that the null hypothesis is false. You can't flip it around, because the p-value is also a conditional probability. Does anybody know what conditional probability? What do we condition on? Yeah? Exactly. Every story about significance testing starts by assume the null hypothesis is true. And that makes it a conditional probability, and that means you cannot just say the chance that the null hypothesis would be true, because we already assumed it to be true. Yeah, it's already the condition. Yeah, so the p-value only gives you one piece of information and one alone, and that is the chance that you get this large test statistic given that the null hypothesis is true, which most of you answered correctly at the beginning. Okay, what happens very often in papers is that people take high p-values to mean that the null hypothesis is likely, and small p-values to mean that the null hypothesis is unlikely. But you cannot make conclusions like this, because you're committing the Bayes rate fallacy. You're failing to account for the fact that there are other unknowns in this formula that you did not account for. So you can only interpret the p-value as the chance of getting this large a result given that the null hypothesis is true. And any other interpretations can lead to decisions which can be costly. Okay, so let me get back to the course in general, and what this thing is that we're actually trying to do so far in the course, which is called likelihood. So p-value also is a measure of likelihood, namely what is the chance of observing the data given the model or given the parameters of the model. Yeah, so in frequentist statistics, which is everything up to this lecture, we assume the model parameters to be fixed. We start by assuming, okay, if this is the right model, and then we ask the question, what is then the probability of observing these data? And if the probability is high, likelihood is high, and if the probability is low, likelihood is low. Yeah, that is the entire concept of likelihood. And you can say if one model was more likely to produce these data than another, then I favor that model. And that's how you do model selection with likelihoods. Yeah, so it's not necessarily wrong, but it has a very particular interpretation. Now, that's not the same as saying, what is the chance that this is the right model, given the data that I've observed? But if you think about it, what is the chance this is the right model? That sounds like a much more interesting question than what is the chance that these are the right data, given this model? Yeah, so That is why Bayesian statistics exist. It exists to apply this Bayes rule to obtain the opposite. And so you can directly say, okay, this model has a posterior probability of, I don't know, 25% of being the right model, for example. Yeah, so it's a more interesting question. That is why Bayesian statistics exists. Now, let me explain to you. Oh, wait, no, wait. Actually, we are already about 40 minutes in. And I'm about halfway through my slides. Let's have a 15-minute break, and then 9 to 10 we will continue. Okay, if everybody could get seated, then we will continue. So, we've introduced the idea of conditional probability, that if you condition on something, you obtain a different probability than the overall rate at which something occurs. Then I said that essentially everything we've been doing so far is based on the principle of likelihoods, which is also a conditional probability, namely the probability of observing your data under your model. So you assume your model to be true, and then you look at the chance of observing your data, that's your likelihood. Now, and then finally I said, what if we could flip it around using that Bayes rule and get an estimate of how likely is this model? Because that is much more often an interesting question. But before I get there, I want to make one thing clear, and that's when I give this is one of the hardest lectures to give because it gives off the wrong vibe. It gives the idea that everything we've been doing so far is the wrong way to do statistics, and now in 1 or 2 hours, I'm going to explain the right way to do statistics, and then after that, we're going to forget about it again. That's not the point. All models are wrong. That's a famous quote, and it goes on, but some are useful. And that is true for frequentist statistics, that is true for Bayesian statistics, because even Bayesian statistics is not impervious to model misspecification. And if you just want to demonstrate a difference in means and use a t-test, why would you go full Bayesian and do a very complicated analysis if the answer is more or less the same anyway? So the point is to use something that works, and I think this pragmatic view of statistics is much more useful for a biologist than a purist view of what is the right way to interpret probabilities and why frequentist is flawed or something like that. So the point is not that what you've been using so far is wrong. The point is that you cannot make conclusions of how likely your model is with frequentist statistics, and you can with Bayesian statistics. Now, okay, so with that out of the way, I'd like to continue to what Bayesian statistics actually is, and that's this. We have this formula here, and I'm going to translate it for you. It says it is the probability of our model given the data that we observed. Now, and the way to calculate it is to plug in what we just learned is Bayes' rule. So that's the probability of the data under the model times the probability of the model. Okay, that looks a little strange. And then we divide by the probability of the data. So, okay, let me take some time to pluck this apart, because just by viewing this, I don't think that anyone would know how to compute any of these probabilities. First off, the first thing in the equation on the right-hand side you already know, because that's this one, right? That is what we've been doing so far in the course. Every model that is fitted anything we've done so far can be fitted with maximum likelihood. And then this likelihood that you obtain, that is what goes in here. Yeah, that is the probability of your data under the model. It's easy to compute, and frequentist statistics ends there. That's all we do. Okay, so we can say, all right, if the likelihood times the probability of the model divided by probability of the data, that takes away one part. Now, what are those other two? All we have to do now is determine what that means, the probability of the model, probability of the data. Now, probability of the model, that's what we call the prior. So why is it called a prior? Remember the base rate fallacy in the example with the breathalyzer test, or breathalyzer, I don't actually know how that's pronounced. You have to multiply by the base rate of encountering a drunk driver. And that's at 1 in 1,000. So in that case, that will be the prior probability of encountering a drunk person, which we use to compute the posterior probability that given the data, given the prior, given the normalizing constant underneath, what is the eventual rate that we now think that this person is drunk? Yeah, so the same goes with your model. You may have previous information. You may have a pilot study, or this may be the second clinical trial being performed. And you can incorporate that information. You can use the information from previous studies to construct a prior probability, so it's a probability distribution for the data that you're going to observe. And you multiply that by the likelihoods. Now, of course, we don't always have a pilot or previous studies. So what do you do when you don't have previous information? That is a very heavily debated topic. But the short answer is that there is a simple, well, relatively simple solution to this, which is to use a non-informative prior. So we use a prior that says, I don't know, could be anything. All options are equally likely. Now, yeah, so about this non-informative prior, this is still nice. This is still a reason to do Bayes statistics, even if you don't have prior information to incorporate, because remember, what we want to do at the end is we want to give some probability of observing our model. And even with an uninformative prior, we can get such a probability estimate. Yeah, but it will be less precise than if we have previous information, and we will get a much sharper estimate for the probability. Okay, so that's two things. We have the likelihood times the prior divided by probability of the data. So that means we're almost done, right? The only thing we need is the probability of the data. Well, how hard can that be? Just take the integral of the top part and then integrate over all possible parameter values. So the probability of the data is the integral of the likelihood times the prior integrated over all the possible model parameters. Yeah, but turns out that's kind of hard to do because integrating over all possible parameter values for all parameters in your model creates that's not one integral sign, that is a bunch of integral signs, and it can very easily become intractable, which means that you cannot do this on paper. So this thing underneath is called the normalizing constant. This is the big problem in Bayesian statistics. How do we get rid of this ugly term? So the normalizing constant, that is the final thing I want to talk about. It's not trivial to solve even for fairly simple models. So even something like ANCOVA or a multiple linear regression, you get a bunch of integral signs, different things have a different parameter space. So the integration is really difficult, and almost always there is no analytical solution. So you cannot compute it. And if you cannot compute this, then you don't know what the denominator is, and you cannot obtain a posterior probability. So that's a bit of a problem. Because of that, let's just ignore it. Let's instead try to compute the posterior proportionally. So we're going to say, okay, up to some constant, which is this normalizing constant, the posterior is proportional to the likelihood times the prior. Now, likelihood is easy to compute, prior is easy to construct, multiply them, and okay, we have something that is proportional to the posterior, which is what we're interested in. Now, okay, then what do we do with that? What do we do with proportionality? That is the last part. We're going to draw samples. There are many algorithms out there that allow you to draw samples proportional to something that you have computed. So even though I don't have a proper probability distribution, it doesn't integrate to one, I can't compute probabilities from, I can still draw samples proportional to this posterior probability distribution. And that means that if I do that very often, then my samples represent a population, and that population is the posterior. So it's a trick to get rid of the normalizing constant by just sampling proportional to likelihood times prior. Now, so we don't know the actual formula, we cannot express it, but we can draw as many samples as we want. 100, 1,000, million, billion, doesn't matter. As long as you have the processing power, just draw enough samples until you are satisfied that when you make a histogram or a density plot, that it looks sufficiently like the actual posterior distribution. Yeah, and then we can compute whatever we want. We can get the posterior mean, the posterior mode, median, we can get the posterior variance, we can look at the 95% highest posterior density, we can compute anything we want using just these samples. So that is the big trick that most of Bayes statistics use. There are other ways to deal with the normalizing constant, but that's beyond this lecture. So, and that brings me to the last part, which is called MCMC. That is the way to draw samples proportional to likelihood times prior. Okay, so why is it called MCMC? We'll get to that later, but the abbreviation is Markov chain Monte Carlo. And the point here, remember, is to randomly sample with a probability with a probability proportional to the posterior distribution. Because we're interested in this posterior, we want to say something about the probability that our model is correct. And the way we're going to do that is just by drawing a lot of samples that should more or less follow the same distribution as the posterior. And then from those samples, if I have enough, if I have a million, a billion, whatever, I can get a very precise estimate of things that would work the same way as if I had the actual function for the posterior distribution. Yeah, so that's the trick. Now, this is what that looks like. This is an MCMC chain. This is part of my master thesis. I wanted to create graphs. So a graph is, let's say you have proteins and you want to know which have a direct influence on which others. You can do that in a graph. So you have nodes, which are the proteins. You have connections between the nodes, which means these two influence each other. Yeah, you can estimate that from data. And well, if you can do that, there's a Bayesian way to do it. And here's then what you get. This is a histogram of the posterior samples. Yeah, so computing the actual posterior is, well, especially for this problem, impossible. But by drawing samples, we get a shape, and you can see, oh, wait a second, I can see where the mean is of the posterior. And I can take 95% of what this encapsulates, and then I have a 95% credibility range. So I can actually compute anything I want using just samples. I don't need the actual posterior. Let's see. Yeah, okay. Okay, and on the left, sorry, that was the left. On the right, we have something else. It's called a trace plot. Can anyone guess what that shows? Okay, so on the left, we have a histogram of all the samples I drew. On the right, it's called a trace plot. We see the actual Markov chain Monte Carlo. We see the chain. So the first sample I got was over here. And yeah, okay, in this case, graph size, but it could be whatever you're trying to obtain a posterior from. A graph was computed of about, I don't know, what is this? 1990 nodes and or edges probably. And the next one was higher, lower, higher, lower, higher. Okay, yeah, and then it goes up and down, and then it more or less turns into noise. And yeah, there's some pattern here, but it more or less converges, right? It more or less stays stable at a graph size in this case of what is that, 2070 or something. Yeah, so that's a trace plot. You can't immediately draw conclusions about your posterior using this trace plot, but it is very important to determine whether yeah, this analysis is actually trustworthy, which is the last thing I'm going to show. Namely, we want two properties from this MCMC, which is why it's called an MCMC chain. First is called the Markov property, which means that every sample in my chain depends on the previous, because that's how the step is calculated. It makes random steps or pseudo-random steps using only the last entry, and should be completely independent of everything before that. Well, okay, that's just how it works. It's called Markov property when something depends on the previous and only the direct previous ancestor. Yeah? Okay, next one, Monte Carlo. You may have heard this from Harold yesterday. No? Okay. Monte Carlo is very simple. It's the idea that when you simulate something, you get a random result. So you never simulate something once. You do it 100, 1,000, 10,000 times. And then you get an idea of the uncertainty of the simulation. Yeah, you never simulate something once, you do it a bunch of time, and yeah, that is like keep putting more coins in the machine. You don't care about one result, you care about the long run average. So yeah, it's like a casino, which is why they called it Monte Carlo simulation. Yeah, so we have a Monte Carlo simulation that has Markov property, and that's why it's called Markov chain Monte Carlo. This will not be asked in the exam. I just wanted to show you what the name stands for. Okay, how does it work? Can't explain that, sorry, that's too difficult. But you can look it up if you're interested, and I can recommend some literature if you are interested in Bayesian analysis. But maybe we can see whether it worked. And that is actually pretty easy to see. This is a converged, or more or less converged, Monte Carlo Markov chain. Oh, yeah, sorry. For many years, I thought it was Monte Carlo Markov chain. It's the other way around. MCMC. This is a more or less converged MCMC chain. This is an unconverged MCMC chain. Can anyone tell me why? Yeah? Yeah, very good. So completely ignore the histogram. You can't tell convergence from a histogram. Look at the trace plot. This one is converged. This one is not converged. It's still going somewhere. It hasn't stabilized around some value, and that means it hasn't converged yet. Now, there is another convergence problem, which is, yeah, this is called autocorrelation. So remember, my perfect ideal MCMC chain has Markov property, where you're basically looking at white noise because the next sample depends only on the one directly previous to it. But you can clearly see this isn't the case. You can see here we have 1,000 iterations, but there is a clear upwards, downward, upward, downwards. So yeah, okay, over the long run it's stable, but if I zoom into 1,000 or 100 iterations, it shows a pattern up and down and up. That I don't want because that doesn't have Markov property. Yeah, and Markov property is important for correct inference in Bayesian analysis. So let me show you two simple tricks that we use with Bayesian MCMC to ensure convergence. This is the first one. This part over here, where it, yeah, had to start somewhere, I can just delete it. I can just get rid of it, and now everything is nicely centered around here. Almost every Bayesian does this. This is called burn-in. This is just letting your algorithm run for, well, how long that depends on what kind of Bayesian analysis it is. In this case, I could delete, I don't know, first 200 or something. And from there on, it's more or less around the same value. That's called the burn-in period. So I have a burn-in period of 200 iterations here. And if I get rid of that, I have a nicer, more realistic posterior distribution. You can also see in the histogram what it would do. It would get rid of this part. Yeah? Okay, I can do something else. The problem I just explained, where if I zoom in, then yeah, there's clearly a downward trend here and upwards and downwards. That's not just one iteration, that's maybe 100 iterations down. That's a problem. We can use poor man's convergence, which is called thinning. Now, thinning is very simple. I just delete everything except for observation number 100, 200, 300, 400. And by yeah, more or less getting rid of everything else, then I have gotten rid of this small scale dependence by just randomly taking, or not randomly, by taking only the 100th or only the 1,000th sample, then there is no longer a structure present and it would look like white noise, which is perfect. Can anyone guess why this, okay, it works, but it's not very practical? Yeah? Yeah. Well, yeah, okay, I get what you're saying. So yeah, this is more of an overview lecture than really the nitty-gritty. But when you do a Bayesian analysis, your algorithm, it cannot start from nothing. It needs a starting point, and you have to supply that starting point. So in this case, I gave it a starting point of, I don't know, whatever this is, 1990. But quickly it moved away from that. Yeah, and moved away to around here, and it stayed around here. So my starting point is the reason that these samples over here deviate from the rest. You're right. You cannot just say, oh yeah, I don't like this part, I'm gonna remove that. I don't like this over here, so I'm gonna remove that. That's wrong. But this first period, the burn-in, that's just to get rid of the algorithm moving away from your supplied starting values to, well, hopefully where it's going to converge to. Yeah? Okay, then thinning, you were correct. If I take every 100th sample, I lose 99% of my samples, which means this is going to take 100 times longer than if I don't need thinning. So yeah, okay, again, I'm gonna skip the technical details, but if I have some other way to ensure convergence, better starting values, different step algorithm, that is preferable to thinning, especially for computationally intensive Bayesian analysis, because thinning means everything takes 100 times as long, at least, which is yeah, not something that you want. Okay, in summary, these are the things that I think you should take away from this lecture. First off, Bayesian statistics combines likelihood with prior information. This is the most important part. You have a prior, which could be actual prior information, like an estimate you got from a pilot study, an estimate you got from a previous study, or multiple previous studies. And the likelihood, that is just what you compute with your data and your model. That is what we've had so far in the course. Bayesian statistics combines them to get a posterior probability. Yeah, so the prior allows you to do two things. First off, you can incorporate existing knowledge. Second, you can model additional uncertainty. Remember, everything up till the mixed model had one assumption we didn't really talk about, but it was there, that all the effects are fixed. Yeah, in mixed models we have fixed and random effects. In Bayesian, okay, don't confuse this with mixed models, but I'm just saying this to make the story complete. Everything is random. Everything follows a probability distribution, and the parameters of that probability distribution can follow their own probability distribution, which is called a hyperprior. It goes a bit further. It says that nothing is really fixed, and what we're doing is trying to find, yeah, some probability distribution and not an actual value. Which is a bit difficult maybe, but the point of that is that it allows you to incorporate additional uncertainty, because you are not sure that your model is the right one, you are not sure that your data is representative, so this additional uncertainty is actually a good thing. Now, also, posterior allows for very fun conclusions that you cannot do with everything we've discussed before this lecture. Like, there's a 95% chance that the true parameter falls within these bounds. Very easy to communicate, especially in a business setting where most people don't know a lot about statistics. That is much easier than to say, well, boss, if I were to repeat this experiment a million times, then 95% of the experiments will yield a confidence interval that contains the real value. So often this is preferable when you want to communicate your results, but there's more math involved. You have to choose a prior, and then people will attack your choice of prior and want to see that it is insensitive to the prior choice, and you have to run an MCMC chain, and it has to converge, and it never really ends. Objective Bayes, which is the true Bayesian way to do things, it takes forever to do a simple linear regression, which is why this course is mostly frequentist. But after this, we're going to see an actual Bayesian analysis, because there are things that you can't really do with frequentist statistics. Another thing you can do, which is really cool, is compute a credibility interval. So that is, if I look at my chain real quick, let's look at the histogram. What if I want to know, okay, 60% of this probability distribution contains what? Well, that's simple. I can literally say, if the 60% is centered around 0, I can say, well, the null hypothesis is covered by 60% of the posterior. This is called a region of practical equivalence, and there are ways to compute it that you can do with Bayesian analysis. You can never make conclusions about probability of the null hypothesis in frequentist analysis. Okay, but Bayesian is not easy. There's way more math involved, and we have to somehow get rid of this normalizing constant. Yeah, for now, we'll just restrict it to MCMC, but there are other things like INLA and, well, some more advanced things. And also, you can only trust a Bayesian analysis if you trust and agree with the choice of prior, because a prior is arbitrary. I can use a uniform prior, but if the parameters should be log transformed, the logarithm of a uniform distribution is no longer uniform. So what is a flat prior? What does it mean to be non-informative or weakly informative? That is something that always raises discussion among statisticians. And yeah, then there's also always people who say, well, if I use a different prior, I get a different result. So your analysis is not objective, which is true. And that makes Bayesian very difficult to do. Well, it makes it more difficult to do in practice. Okay, and of course, if you use MCMC, you need to check for convergence. We went quickly over that with the trace plot and things you can look for like trends and local trends like autocorrelation. But yeah, there is more to it. It's a pain in the neck. So, are there any questions? I'll bring the summary up again. Yeah.
Base your prior on previous data like pilot studies and such.
Um, okay, so then the previous study also needs a Bayesian analysis. So the previous study, what you do first is you create a non-informative prior for that, like a flat prior that doesn't have any preference. Then you compute the likelihood, and then with some way, maybe analytically, maybe MCMC, you compute the posterior. That's a probability distribution. And you take that posterior as the prior in your next study. Does that make sense?
Yeah, it's a chain.
Exactly. Yeah. Yeah. And that's. Oh yeah, I didn't say this last bullet point. So that's what's called Bayesian belief propagation. The idea that we have previous data, we have previous analyses, we can use that as a starting point and update our belief instead of always starting with a fresh sample and always, yeah, claiming ignorance. Yeah, so it's one of the strengths of Bayesian analysis. All right, then, yeah, if there are no further questions or if you want to discuss afterwards, of course, okay, I would propose that we have a 20 minutes, should that suffice? Yeah? Okay, let's do a 20-minute break because we have to change the setup here, and then we'll continue to the lecture of Bastian and Friesenor.